When the first direct image of a black hole was presented to the world, it made headlines across the globe. Take a close look at this image. You see a blurred, intensely bright ring of orange and yellow light encircling a pitch-black center. But according to the rules of basic astrophysics, nothing, not even light, can escape the gravity of a black hole's event horizon. This creates a paradox. If a black hole traps all light and remains completely invisible to our telescopes, what exactly is glowing so brightly in this picture? The image captures extreme space-time phenomena occurring just outside the black hole. That glowing ring consists of light caught in a highly specific cosmic mechanism. To understand what we're seeing, we have to trace that captured light backward from the lenses of our telescopes to its exact point of origin. If we ride that beam of light, reversing its journey across 55 million light-years of deep space, we eventually reach the host galaxy, M87. At the end of this journey lies a unique geographic zone near the black hole, where the normal rules of light and geometry collapse. As we descend past the outer accretion disk, the swirling mass of superheated gas, we approach the dark center. At the absolute core lies the event horizon, defined by the Schwarzschild radius, the exact mathematical line marking the point of no return. This spatial map plots the anatomy of a black hole, showing the event horizon here. Moving outward to exactly 1.5 times the Schwarzschild radius, we hit a secondary boundary. Normally, light travels straight. Here, extreme space-time curvature forces light to bend into a perfect continuous circle. This region of space is the photon sphere. To understand the physics here, imagine standing directly on the photon sphere and looking straight ahead. This top-down geometric view shows the result. Because light is forced into a full 360-degree orbit, the light reflecting off your back would travel completely around the black hole and return directly to your eyes. The photon sphere is the only place in the universe where looking straight forward allows you to see the back of your own head. The physics of the photon sphere are governed by a concept called dynamical instability. When a planet orbits a star, gravity is corrective. If the planet is bumped slightly, its orbit remains stable. This diagram illustrates a photon locked in a temporary, perfect circular orbit on that boundary line. A slight nudge inward causes total failure, spiraling rapidly down across the event horizon. If nudged outward, it breaks the gravitational hold, slingshotting into open space. The photon sphere is a razor-thin tipping point where gravity and the fastest thing in the universe battle to a draw, right up until the light is either consumed or liberated. That outward nudge, that moment of liberation, is what connects this extreme physics back to Earth. The photons that fall inward are lost forever, but the ones that get bumped outward are the exact particles of light that travel across the universe to strike our telescope lenses. This highly focused, bent light escaping from the photon sphere makes up the bright ring we see in astronomical images. This accumulation of orbiting light marks the absolute inner edge of the visible accretion disk. The dark shadow in the center exists because the photon sphere bends and focuses the light around it, framing the invisible void of the event horizon. Look at the original photograph again with this new context. We are looking at a precise mathematical boundary. Every single pixel of that glowing orange circle represents light that spent time trapped in an unstable orbit, escaping by the absolute thinnest of margins before it could be swallowed. The photon sphere is the exact tipping point where gravity and light reach a stalemate, ultimately allowing us to